Okay, so here's our big question. Our average squared deviation for this line is 0.52. Can we do better? Now I've put the points in orange, and I'm going to indicate that let's go, how about this? Let's go ahead and put a line through here that comes closer on the average to all the points. Now, whether that comes closer to the average, you're going to have to determine by making some estimates. But based on the estimates of our coordinates and on all the other information we have here, I'm going to suggest that you should try to obtain the equation of this line, remembering that the equation of the original line was y equals 5.2x plus 0.48, and see if that line does a better job of fitting the data in the sense of giving you the better average deviation or the better average of the squared deviations, which is now kind of off the, well, I guess you can still see it. Can you see it? We got the 0.4. I had a little trouble reading the screen. Yeah, there's our 0.52. Okay, so it's still there. So can we improve on this by putting the point kind of in the middle of the distribution rather than just going through the first and last points? What's your estimate of the straight line, the equation of the straight line corresponding to the orange? Okay, my estimate would be, it looks like the y-intercept is about half of what it was. So the y-intercept was 0.48, so I'd say it's 0.24. And let's see, if we go over 1, 2, 3, 4, 5, 6, it looks like the y-coordinate is pretty close to 3, maybe a little over 3, maybe even 3.24. I'm going to say the rise from here to here is about 0.5 with a run of 0.6. So I might estimate that line to be, and where's my orange chalk? Got to pause for a second. Okay, so just eyeballing this, I'm thinking that's about 0.5x plus 0.24. And I suspect that that's going to decrease the average of the squared deviations by some quantity. Okay, now you should make your own estimate. And maybe you should make your own estimate by choosing 2 points on this line. And let's say no fair choosing the y-intercept. Let's choose some y-coordinate between 1, or x-coordinate between 1 and 7, and estimate the corresponding y-coordinate. For example, don't use my example, but if I chose y equals 2, okay, then it looks like the point might be 2, 1 on that line. So maybe we have the point 2, 1. And if y is, oh, let's just go with 6, and let's go up to this line here. And I'm thinking that looks like about 6, 3. Okay. Then the slope and so forth would be what they are, but using the y equals mx plus b as we did before and solving the simultaneous equations, what equation do you get? How does it compare with my estimate, 0.5x plus 0.24? Okay, that might be a better estimate. Make your own estimate using 2 different x-coordinates, not 2 and 6. Make your own estimate, run through the simultaneous equations, and see what your model is. Then run through this entire process and see what your average squared deviation might be. Note also that I didn't take the square root of the average squared deviation as I would if I was calculating a standard deviation. All I'm trying to do is make the average squared deviation as small as possible. So if the average square deviation is as small as possible, well, so is the square root of the average square deviation. I'll add a little more information. For this line, where I said I thought that this would significantly improve the average square deviation, I get the average square deviation to be about, I believe, 0.24. Let me just make sure about that. Yeah. So here, the average square deviation is approximately 0.24 for this model. See if you can improve on that. And the 0.24 here is just coincidentally the same as the 0.24 here. They have nothing to do with one another, except, of course, the more accurate this is, the more accurate this is going to be, or the smaller the average square deviation is going to be. In any case, it should be clear that going through the first and last points is not a very good strategy for finding the best straight line. We have to manipulate the line and try to minimize the distances between the line and the data points. Now you should go ahead and maybe verify this, make your own estimates of 2 points on the line, see how your average square deviation can be minimized.